Good evening to all. Today I am going to discuss about FET amplifiers. In previous video, I updated about BJT amplifiers. And today we are going to discuss about FET amplifiers and some of the few biasing methods of FET amplifiers. So this is the general classification of FET. So in general, transistor types, there are two types of transistor. First one BJT, bipolar junction transistor, and second one field effect transistor. So in BJT, based on the structure, based on the construction, it is classified into two types, NPN type and then PNP type. In field effect transistor, it is classified into junction field effect transistor and then metal oxide semiconductor field effect transistor. So under JFET, again it is classified into two types based on the modes. So first one in JFET, it consists of only depletion mode. So it is classified into N channel and P channel. In MOSFET, it is classified into two modes. One is depletion mode and then enhancement mode. So under depletion and enhancement mode, it consists of two channels, N channel and as well as P channel. So this is the entire classification of transistors. And this is the difference between the BJT and FET amplifiers. First BJT, so both the transistors it consists of three terminal semiconductor devices. In BJT, the terminal consists of emitter base collector, and in FET, the terminal is denoted as source, gate, and then drain. So BJT is a current control device and FET is a voltage control device. So it is a bipolar device and FET is a unipolar device. So based on the structure of the transistors, it is classified into two types, NPN and PNP type, and in FET it is two types, that is JFET and MOSFET. And next one, construction of JFET. So based on the construction, so it is classified into N channel and P channel. So here the direction of the current takes place. Here it represents from gate to source. So the symbol representation, the arrow mark representation is the difference for the N channel and P channel FET. So in general, FET consists of three terminal. First one, input. So input terminal is always the gate terminal and we are taking output only in the drain terminal. So the drain current consists of so the drain terminal consists of drain current. It is denoted as ID, and source terminal. So based on the requirement of the biasing method, we can utilize the source terminal. And this is the P channel type of FET transistors. So both the N channel and FET transistor, the terminals are same. And this is the general construction of N channel JFET. So it consists of PN, two P regions and one N region. So N is represented as drain and P layer is denoted as depletion region. So that is, it is connected to the input of the transistor, and another region is connected to the source of the transistor. And this is the general JFET drain characteristics of the amplifier circuit. So based on the drain to source voltage and the drain current, the characteristics has been structured. So based on the VDS and ID value, VGS value is presented. So there are conditions for the drain current and as well as VDS. So it consists of three regions. So in BJT, we discussed about three regions. One is cutoff region, active region, and then saturation region. Similarly, in FET amplifier, there are three regions. One is ohmic region, and then pinch off region, and another one is breakdown voltage values denoted in the another part. So based on this and based on the VDS value and ID value, corresponding VGS value will be plotted, and from this we can plot out the load line and as well as Q point of the FET amplifier transistors. So this is the first condition. So first one, when VGS is equal to 0 and VDS is equal to 0, at that time we are calculating the drain current of the FET amplifier. And next condition, when VDS is equal to 0 and VGS is decreased from 0. And so the corresponding VGS value and ID value will be denoted in the characteristics. And next condition, when VGS is equal to 0, at the time the VDS is increased from 0. So this is the main conditions for plotting the JFET drain characteristics. And next condition, when VGS is negative and VDS get increased. So here see, here the VGS value is negative. So at that time the VDS value get increased. So based on these four conditions, the drain characteristics can be plotted. So for plotting the drain characteristics, the VGS and VDS is very important for plotting the load line and as well as Q point of the JFET transistors. And next one, characteristics of parameters of JFET. So we know that the general classification of amplifiers. So first one, transconductance, voltage amplifier, current amplifier, transconductance and transresistance amplifiers are there. So based on that, here for JFET, the parameters are calculated. So first one, transconductance. So in general, transconductance is denoted by the symbol representation GM, and drain resistance is denoted as RD, and drain conductance is denoted as GD, and amplification nu is nothing but amplification factor. So based on the VDS value and VGS value, the ID value will get different. So by using these conditions, the corresponding transconductance term, drain resistance, and then GD value and amplification factor will be taken from the general values. And next, this is the relationship among the FET parameters or relationship between mu, RD, and GM. So mu is nothing but amplification factor. So ID is nothing but drain current. So for calculating the drain current, we are using some theorems. So these are all some few theorems, Taylor theorem, by considering the VDS value, VGS, and then ID value. So first, we are calculating the ID value. And then next, this is the characteristics. Based on the characteristics, we are plotting the ID value. So ID value is based on the VGS value and VDS value. So first, the Shockley equation becomes for the drain characteristics, that is IDS by IDSS is equal to 1 minus VGS by VP whole square. So this equation resembles the equation of parabola. So we know that the equation of parabola is given as y equal to x square. So we are writing the drain current in terms of the equation of parabola. So we know that ID is the drain current. So IDS is nothing but saturation drain current. So therefore, IDS is equal to IDSS into 1 minus VGS by VP the whole square. So this is the drain current equation for only the JFET amplifier, and for MOSFET amplifier there is a different ID value for the MOSFET amplifier. So by using this VGS and then IDS value, the characteristics has been plotted. So this depends upon the drain current and then saturation current and then source current. So based on the source terminal, drain terminal, and then gate terminal, we are plotting the values for VGS and then IDS. And next comes to the biasing methods of FET. So these are all some few biasing methods of the FET amplifier. So FET is classified into two types. One is JFET and next one MOSFET. In JFET biasing circuit, there are three types of biasing methods. So one is fixed bias, voltage divider bias, and then self bias. In MOSFET biasing circuit, it is classified into based on the depletion mode and then enhancement mode. It is classified into two ways. One is voltage divider bias and then self bias in D type. And next one, in E type MOSFET biasing, there are two types. First one is voltage divider bias and then feedback configuration. So this is the general biasing methods of the FET transistor. So these are all the few current relationships of the FET amplifiers. So that is JFET and then MOSFET. So for all the FET amplifier, so this is the main conditions. We are going to consider Ig. So Ig is nothing but gate current. So Vg is nothing but gate voltage. So from the gate voltage, we are calculating the Ig. So for FET circuit, we are going to assume the gate current Ig is equal to 0. And then next, drain current is taken from the drain terminal, and Is is taken from the source terminal. So the drain current and source current almost always will be equal in the FET amplifier circuit. And next, for JFET amplifier, so this equation in previous slide itself I discussed, that is the drain current for JFET and D type for MOSFET is same. So for JFET and as well as for depletion mode type MOSFET, the drain current is common. So ID equal to IDSS 1 minus VGS by VP whole square. And for E type of, that is enhancement mode type of MOSFET, so ID value will be different. So ID equal to K into VGS minus VT whole square. So K is equal to constant. Gate to source voltage is denoted as VT, and VGS. VT is nothing but thermal voltage. So this is the current equation for JFET and as well as MOSFET. So first I'm going to discuss about the fixed bias method present in the FET amplifier. That is in JFET amplifier. So this is the general circuit of fixed bias circuit in JFET. So in fixed bias circuit, in previous BJT also we are putting the emitter is grounded. So similarly, in fixed bias circuit for JFET, we are going to considering the source terminal going to grounded. So first, gate is nothing but input terminal, drain is nothing but output terminal. In gate terminal, we are connecting supply voltage, that is gate to gate voltage. It is denoted as VGG. So here based on this connection, the polarity is mentioned plus and minus. So the current conduction takes place in the clockwise direction. So the Ig, so our current value is denoted as Ig. And next one, gate to source voltage is denoted as VGS. And in the drain terminal, the resistance is connected. So it is denoted as RD. So in drain current, it is denoted as ID, and supply is connected in the drain terminal. It is denoted as VDD. And then next, from drain to source voltage, the voltage is denoted as VDS. So this is the simple fixed bias circuit of the FET amplifier. So in first step, from the fixed bias circuit, we are going to calculate the voltage value. So that is VGS and then VDS. And then next ID is constant for the JFET amplifiers. So we know that from the step 1, we are going to analyze only the gate terminal. So previously in BJT also I discussed for all the biasing methods, we are going to calculate the current and voltage value by applying KVL to the each and every terminal. So in same way, we are going to applying the KVL rule for the gate terminal and as well as drain terminal. So first in step 1, I'm going to considering only the gate terminal. So it is denoted as, so from this we are calculating the input voltage. So we know that so in gate terminal, we are having only two voltages. One is VGS and then VGG. So therefore, in step 1, VGS plus VGG is equal to 0. So we can write this as VGS is equal to minus VGG. And next in step 2, we know that current value for the FET amplifier, JFET amplifier is constant. In the previous slide itself, I discussed that the current value is same for all the biasing methods present in the JFET amplifier. And next step 3. In step 3, we are taking only the drain to source. So we know that source is already grounded. So we are going to apply KVL from drain to source. So we know that we can write the equation as VDD minus IDRD minus VDS equal to 0. So from this equation, we can calculate the VDS value. So therefore, VDS is equal to VDD minus IDRD. So this is the simple fixed bias circuit for the JFET amplifier. And then next, voltage divided bias. So in voltage divided bias, similarly, the circuit consists of R1, R2 resistor, and coupling capacitor C1 and C2 is denoted as coupling capacitor. So the main function of the R1 and R2 resistor is it acts as a potential divider. That means the circuit, the R1, R2 which applies the fixed voltage to the input terminal. Here the input is nothing but gate terminal, and then RD. RD is connected in the drain terminal and RS is connected in the source terminal, and corresponding capacitance value is connected in the source terminal. And we are taking output in the drain terminal. So supply is connected in the drain terminal. It is denoted as VDD. So in same way, we are going to calculate the VDS for the voltage divided by us. So therefore, we are applying KVL to the drain to source voltage. So consider the drain to source voltage. We can write the equation as VDD minus IDRD minus IS RS equal to 0. So from this equation, we can write VDS is equal to VDD minus ID. So in previous one slide, I discussed that ID equal to IS. So we are taking that element as common, and we are taking the drain current as common value, and we are making the resistance value or as RD plus RS. And from this, we are calculating drain voltage separately. So VD equal to VDD minus IDRD, and source voltage Vs is equal to ID into Rs or Is into Rs. Both are equal. And next, we are taking the current value in resistor 1 and resistor 2. So both are equal. So we can write the current value as VDD by R1 plus R2. And we can write the base voltage VB equal to VDD into R2 divided by R1 plus R2. So this is the voltage and current equation, and output voltage drain to source voltage equation. So this is the main thing we are calculating in the voltage divided by a circuit, that is VDS. And next one, self bias. So in self bias circuit, we are taking the gate as input and drain terminal as output, and source resistor we are connecting the source resistor, and we are connecting the RG in gate terminal. So we are considering the gate to source voltage, it is denoted as VGS, and drain to source voltage is nothing but VDS. So here by using the ID value, we are plotting the Q point. So in previous slide itself, I discussed that based on the VGS value and then VDS value, ID drain current will be calculated, and based on the ID value, we are plotting the Q point and as well as the load line in the JFET characteristics. So in same way, we are calculating VDS. So for calculating VDS, we are applying KVL to the drain loop and as well as in the source loop. So after applying the KVL, the VDS is equal to VDD minus ID ID into RS plus RD. It is same. It is similar to the voltage divided by us. So up to this, FET amplifier is over. In next video, I will discuss about the MOSFET biasing circuits. Thank you.